Maybe I will just wait for 2 minutes next, and I will start. Okay. So all the CRs, please do it. Huh? I don't know why some of you are okay. Maybe some of you are joining. So the CRs of IT, CS, and electronics, right? All of that means most of you have joined. Or there is anyone remaining to join online? Because I have given the online. I think that was almost 2 hours ago to all of you. So the CRs. So shall I start? Because if I start, I will not able to make the joining. This is a problem in Google Meet. You cannot just see that who is requesting to make a join. Okay. So is it okay? I can start, all of you.
Yes, sir.
Okay. Right. All of you are present, right? Electronics, computer science, and IT. All of you are present, right?
Yes, sir. Electronics science present.
Okay. The computer science students, are you there?
Yes, sir, we are present.
Okay. Okay, BTech IT, I'm saying some of them. Okay. Let me start, okay? So, just one sec. This is the problem. Again, one is joining. So why don't you join in the online also you take delay, in the offline also you take delay? I don't know. That means what is happening for the CU students? Offline, you tell it's a delay due to the traffic and all these things. In online also you join delay. You joined lately. What is this? I don't able to understand. That means what this amount of sincerity, punctuality. Okay, right? I mean, if you don't have at this level, right? I think MSCs are final year. BTech are also close to final year. Just the pre-final year. So I don't know. That means why you do like this. Okay, so still I think around 30 students are less, but it's okay. Maybe people are engaged in other things today. Maybe some puja is there, but still I tried to finish between 12. See, still people are joining. So I will not able to join further. Okay, let me move on. So I hope that everyone can see my slide. First slide.
Yes, sir.
Okay.
Yes, sir.
So we are just giving some. Okay, today's lecture will be on fast Fourier transform, and then see this is the problem. This is the problem. You can't be systematic. Students will not make you work systematically. That's so bad. It should be systematic. You should 11. I have given you all 15 minutes. 11, 16. I'm just starting the lecture online, and still you are taking time. I don't know how you will manage in the present day. I don't know. If this is the approach that I have. So I will not join anyone from here because I cannot break my continuity of my lecture. Okay. So the first Fourier transform, obviously, I just a recapitulation. I think all of you have gone through this discrete Fourier transform, which clearly speaks, and this has been well discussed in the class, that how you generate the xk, which is the Fourier coefficients. And I'm not getting into this. These expressions are already known to you, and you have studied those. Okay. So let's move on. So the DFT has n square, complex multiplications, additions. So for very large n squared is pretty high. So can we do something better? And if you want to do something better, then obviously the first Fourier transform is one of the algorithms which makes you under O n log n, and that is a massive compression. Okay, and if n equals to 1024. Okay, it's called 1024 DFT, 1024 point DFT, which is number of n, the number of samples define the point FFT DFT. So 1024, if you have 1024 samples, FFT is 100 times faster than DFT, right? And it goes on higher and higher when n is more. So you know that if you trying to analyze a speech signal, okay, 4 hertz, audio signal, 20 hertz, right? You know how many samples. 20 hertz means, okay, sorry, 20 kilo, 20 kilohertz, sorry, 4 kilohertz and 20 kilohertz, okay? So it's so many samples, right? Only a simple audio, right? And that you will do a tremendous gain in FFT by doing n log n compared to n squared, okay? So let's do this. We have already discussed a bit on this, okay? So basically, when we try to define this, it's a Cooley and Turkey algorithm on 1965, which I have already explained a bit of this in the previous class, that we try to define n into 2 subsamples. One is the even index samples, one is the odd index samples, okay? And then we combine the results. So one part of x is xk is e to the ek plus w n k dot ok, and other one is xk plus n by 2 ek minus w n by k ok. And this is something which is there. Ek is the DFT of even samples, okay, right? And k is obviously, when we tell k is obviously here 0 to n by 2, okay? So k is 0 to n by 2 minus 1. Okay, so basically the first sequence is, okay, 0 to n by 2, and another sequence is n by 2 plus, okay, the next half. And wkn is wkn means k is the superscript, and capital N is the subscript. So it is e to the power minus j 2 pi capital N into k. Okay, so only the k will vary with each of the components. Okay, so this actually repeated recursively, okay, unless you reach a DFT of size 2, which is trivial to compute. Okay, and this algorithm is basically so that, and there are a few things you have to leverage. One is symmetry, which means that wnk plus n by 2 is equals to minus wkn. Okay, so it means that it's a symmetry. Okay, which means that, okay, k plus n by 2 is basically something which is minus. So okay, so which means that if we look into the value of k, okay, k is the sample, number of sample. Okay, so it means that the one half is exactly that means this. Okay, this particular wk component, okay, acts in a symmetrical way. So what we have in one half, it's just the inverted form in the other half. Okay, and periodicity means after capital N it repeats. Okay, so k plus n and k is same. These are the things which we used it in computation. So okay, so these are the precondition. FFT works best on input length capital N is in power of 2, and this is the thing of DFT. So there are steps. First step is, so if you look into the steps of FFT, obviously we have to first compute the Wn, which is e to the power j 2 pi n, okay? And we have to understand, and we have to read the sequence. Then what you do, we split xn. These are the steps, okay? Try to remember, these are the steps. Try to remember that we will split it into 0 to 4 and 1, 3, m, okay? Where we know that the first part, which is x to m, is the even indexed, and x to m plus 1 is the odd indexed, right? And the total xk is being defined by this way. This is the form by which xk is defined, and that is already being discussed. Okay. Now we have to compute two DFTs of size capital N by 2, and then we recursively do this.
Okay.
Then this particular sample, this particular sequence is again split into even and odd. This is again split into even and odd, and again this goes on unless we reach to the length of the sequence where we have two elements. Okay. So this is a recursive way of to do it. Okay, this is the ek and this is the ok. Okay, so this is xk, right? And then there is a xk plus n by 2. Combine the step butterfly operations. So we need to do this for k. As I say, k is from 0 to n by 2 minus 1. Okay, and ultimately the two point DFT is trivial, right? If it is x0, it becomes x0 plus x1, and if it's x1, it becomes x0 minus x1. So this is very trivial, which means that this is capital X0, right, and this is capital X1. Okay, so this is very trivial. So this is what is there, and so ultimately there is a bit reversal. This is very important. There is a bit reversal. So basically we will have the normally we will the 0 0 0 will have a reversal of bit reverse like this. So now the 0 decimal has become 1 decimal has become 4, 2 has become, so this divided corporate efficient implemented iterative in this algorithm. So this bit reversal occurs, which we have to again take into the which we have to take into consideration the bit doing this operation. Okay. Now let us take an example. Suppose we have a string. This is an example. We have a input time domain which is 4 ones and 4 zeros. Okay, so the indices are 0 to 7, and we reverse the bit. So which means that so this bit reversal means that the index 0, the FFT for index 0 will be in the index 0 of the output. And index 1, FFT will get in the index 4 of the output. Index 2 will be get in the index 2 of the output. Index 3 of the input will have the FFT value in the index 6. Index 4 will have index 1. Index 5 will be in the 5. Index 6 will be in the 3. Index 7 will be in the 7. So this is just the bit reversal. Means if you have the indexes, binary combination is this. When we go to the output, you just actually reorder the reverse order the binary index, and that index will be the corresponding FFT. So that's the only thing you have to understand here due to this operation. Okay. So we know that if you look into this bit, there are 0 to 7. There are binary 0 to 7 of the index. So the logic is that we will have 0 to 0. We will have 1 in 4. We will have 2 to 2, 3 to 6, 4 to 1, 5 to 5, 6 to 3, 7 to 7. This is what we will have. Okay. So now what we do, we actually so that this output sequence is as per the actual input, right? In the input we change it. Okay, so input, what we do, right? In the input we just reorder this. Okay, so that x0, x4, x2, x6, x1, x5, x3, x7 is the actual sequence instead of the actual sequence what we have, because we know that if we give this actual sequence, then we actually get 0, 1, 2, 2, 3, 4, 5, 6, 7, 8 as per the order in the output. Okay, so as per the bit reversal, we generate this sequence in the X. Okay, is there any confusion in this bit reversal? Anyone? If you have any confusion, let me know on this bit reversal. Okay, so we have to reorder the indexes in the input just to accommodate the bit reversal which happens during the operation, so that this bit reversal taken care of the input will make me the output taken in the actual order will give the corresponding FFTs of x1, x2, x3, x4. Okay. So what we do now, we actually try to understand this particular WKN. Okay. So this is the array. So what will be a butterflies of size 2, m equals to 1. So we will have the, okay, so 2 point, we will have to generate the EK. So the pairs are 1 0 1 0 1 0 1 0. Okay. Okay. So each pair yields 1 plus 0 1 minus 0 1 1 for the first pair. So after stage 1, it will be all 1 1 due to this particular data. Okay. Now stage 2, butterflies for size m equals to 2. So we have to have the twiddle factor. So we generate the twiddle factor for this. So what we do, we generate this equation. Okay. So this is J. So we generate this equation, which is actually this one. Okay. EK plus WNK. Okay. Okay. So, okay. So we actually generate this W values. Okay. And we try to, okay, we try to go with this. We generate this, if we, okay. Yeah. If we try to, yeah, so yeah, so if you try to yeah, so this is the expression, right? EK plus W and K, okay, right? And what is okay? Okay was something like this, EK and okay. So this we have to generate. XK we have to generate, okay, which is X2M into this plus this plus X2M minus M plus 1. So this is 0 and 1. All the 2 blocks you have to understand. This is 0 and this is 1. Okay, so if you do this, I think if you compute this, right, you will get these values which has been generated. Okay, and then now combine the 2 4-point results into full 8-point twiddle factor. Now we will, so what we did, we actually, first of all, we did in a sort of bottom-up approach. So what we did, okay, we did it between the 2. Okay, so instead of 0 2 4, we did between 0 and 1. Okay, for each of them, each of the blocks, 0 and 1, 0 and 1, we split it. Okay, and then we generate this, right, and then we again generate the next level, okay, of group of 2 to group of 4, group of 4 to group of 8, like this. Okay, right, and each of the generation process we will use this term. XK will be something like this. Okay, so that we actually did. We actually generated first this 2, and then we generated butterflies of, butterfly means these operations is a butterfly operation. These operation, okay. These operation is a butterfly operation. Okay, and then we again do it for actually that means your capital N equal to 8. Again we generate the twiddle factors and again we expand it. So this is the way we generate this, okay, this capital X, and we will have this X1, X7, X3, X5, the odd ones, and so the process will be something like this. Okay. Okay, so we first fit it to 2, then we fit it to 4, then we split it to 8, right? And if you want to look into the more on the circuit, let me try to find if there is any more PPT here. Let me see if I have something. Yeah, so this is the scheme. What is bit reversing? You have to understand that. Okay, so we have to do with X0, X4. x2, x6, x1, x5, and x3, x7, which will generate an ordered output of x1, capital X1 to x4. So this we expect in the example also. Okay. So we have to do this, and these are the things we did actually in the same thing we did. Okay. This is AK and BK. So it is one is XK is AK plus WNBK, and this is the second part, which is AK minus WNBK. So if we try to look into here, see these are your X or even, these are your X odd, okay? Right, and what you are doing here, these are all, here capital N is 4. And these all will be changed, okay? Because this is capital, small n will change here, okay? The small k will change here. These are the capital N. Capital N is 4, so W4 all over. And the small n will change according to this. Because if you look into this, it is W capital N is your suffix, and small k is your prefix. So whenever you are generating this as a capital X0, so you have to, accordingly, we have to adjust the W factors here, and you will see that how it works out. It works out that this one, the even one is WK plus BK. So you see that this is AK, right? So okay, so here what happens is that, okay, if you see that, okay, this is this particular plus. The plus what you do here, AK, WN, K, BK, this plus is represented like this. So we have 4 additions, okay, right? And here it is a subtraction. Here it is a subtraction. Here all are subtractions, okay? So in the odd part there is a subtraction, and that works well. And you see that, okay, so plus and minus, it works, and that it generates all the states, okay? Let me see if there is one more. I think I should have, but let me see. Yeah, here also you will see the thing what we discussed, right, is being shown here, and yeah. So these are all things will be fine to help you. I think I have one more, maybe. Oh no, this one. Okay, sorry. Yeah, I think this is all. I don't know that there is something there. Okay. Fine. So these lectures I will upload. Okay. So try to work it out by hand. I think all of you will get this done with this mathematics which are given, right? I haven't used the board, so okay. So might be okay. That means it would have been. That means I will go by step by step. Yeah. So I will push up all this. I will push to all of to all this mathematical these examples for FFT, and you can work out on your own. And if you have any difficulty, we will try to come up in the next class. But I think the next class will be most probably after puja. If I don't visit this IBM event, right, I stop this IBM event. That I don't visit the IBM event, then I will let you know that if I'm taking the class on 24th. Okay. So yeah. So the suggestions, and all other students can also, that means I can put up the question paper what I've given in the mid-sem for the IT as an assignment. Okay, for the other students for okay, from computer science electronics, just to make your make your practice on those questions. Okay, because they have already, the test has been given by the BTech IT batch yesterday. So let us finish this brief lecture today. I just thought to explain you some of the FFT examples and FFT computations. Okay, and from next class I will start on discussing on the filters, or maybe after puja. So filters I will take 2 classes. Then I will take Z transform. Then I will go to a little bit of image processing, right, on the thing. So I think maybe 5 to 6 classes more will finish my course. Okay. So thank you all for joining this brief lecture. Okay, and right, and I will let you know of the next week. Okay, and any questions you have, you can just ask me today, or you can now, or you can ask me also. Okay, in the Google Classroom if you have any difficulties understanding. Okay, but try to yeah, I will upload these PPTs and try to go to the mathematics by hand. I think you will get it done. Okay. Any questions? Any one of you?